So I will have to apologize for doing a bait and switch on you. I decided at the spur of the moment to change up what I was going to talk about today. What I was planning to talk about today was some of the philosophical background behind thinking about fairness. But I've been talking to all of you, in various situations, and I've realized that there's another topic that I was going to cover later on, but that may be better to cover right now. And this is the topic of accountability. And I think this topic is interesting because it takes us a little, it's related to the things I've covered before, the topics of fairness, but it's also more general. And I think it's something that might be useful to you, even if your concerns have nothing to do with fairness at all. This is a way to probe models and understand your models in a way that I think will be very useful. And it also does relate to fairness as well. So I'm going to change that, and we'll get back to sort of these underlying philosophies of fairness later on, probably towards the end of the course when we're already exhausted about thinking about mathematics, and this might be an easier thing to think about at the time. So what is this problem of accountability, right? And so let me try to define what that means. So while we've spent a lot of time talking about fairness definitions and fairness preserving mechanisms, the major goal was to determine, is this algorithm doing something that is unfair? And the way we've tried to characterize the idea of unfairness was to say that the decision made by the algorithm was in some way influenced by certain variables that we don't think it should have been influenced by, right? So we have some decision-making process. It takes a bunch of inputs. There's one particular feature of the input that we don't want the algorithm to be influenced by, either directly or indirectly. And so we've done all this work to make sure that somehow explicitly or implicitly we can remove the effect of this feature from the data. But if you think about it, you're asking really a more basic question. Right? What is the influence of any variable on the decision of the algorithm? I mean, there might be these special features that we worry about, but there are also other features that may not be special but might be relevant. And then you can say, okay, how much effect do these features have on the decision made by the algorithm, right? And so this is the problem we're going to be talking about for the lecture today, right? And I'm going to, so I said that this is the general area of accountability, which was I realized I had made a mistake in my title of the course, but really this is the A, not accuracy, which is, and accountability means many things, and it's a kind of a fuzzy word. It means responsibility, it means liability, it means all kinds of things. In the specific context of today, what I mean is by accountability is going to be influence estimation. Okay? And towards the end, I'll briefly throw out some notions of what accountability might mean apart from influence estimation itself. And so here's the abstraction that we will be considering. We have some black box, right, which computes some unknown function of x1 through xn. Okay? So the input comes here and comes out here. This is what this black box is doing. Right? We don't know what it's doing. And now we want to ask, okay, this is the thing we're asking. How much influence does any particular variable have on the outcome? Now, of course, you can see why a solution to this would be a useful tool to detecting bias in machine learning. Because you could say, okay, I built some learning system, I apply some magic tool that I have from here. It says, oh, this feature, the cost of the individual is having a major effect on whether they get a loan. I'll say, okay, well, that doesn't seem right. We don't want that to happen. Let's go look at this some more. Right? So it gives you a diagnostic tool to go and investigate what your model is doing. And this is why I'm saying that this idea transcends discussions of fairness. It's a much more basic way of probing a model. And if you do any kind of work with machine learning, this is something that you should be thinking about doing, because you want to say, look, I'm building this model, it's making predictions, but I'd like to know where the predictions are coming from. What seems to be driving the predictions? Okay? When we talk about interpretability, another way of dealing with this is to make this black box very nice and clean and open and white. Make it a simple box that you can understand. But today we'll say, look, okay, I stuck my, this neural network is working great. I don't want to tamper with it, but I'd like to understand what exactly is going on with it. So this is the problem we'll be looking at. And we'll be looking at different ways of thinking about this. Okay? So this idea of trying to estimate the influence a variable have on its function, not surprisingly, is a very old idea. It goes well back before any of the things that I'm talking about right now. Right? In fact, if you look at work in economics and social choice theory, this question has been asked where this, so this dates back to at least the 1930s and 40s. Social choice theory is the theory of how communities come together to make decisions. So, for example, how do you design a voting scheme? Right? Voting schemes like the ones we have or other kinds of voting mechanisms are part of the subject of study of this area, because you're looking at how collectively choices are made from individual preferences. And so one natural question that people ask is, well, how much power does an individual voter have? Now, you often hear when an election comes, well, you have only one vote. What good is your vote going to be? Right? Of course, the paradox here is that if everyone says their vote is useless, then in fact something really bad might happen. Right? So even though one individual vote on the surface may not seem useful, there is some kind of collective influence that happens with your votes. And so the question you can ask is, well, if F is a voting scheme, then the input to F are the votes of individuals, right? So Xi is you. So this is really asking how much influence you have on the outcome of the vote, and how do you design a voting scheme so that everyone has some reasonable influence on it. So this question of influence is a very basic question, right? It's not just a machine learning question or anything like that. It goes back well beyond. And even within the realm of machine learning, and this dates back to the 80s, people have looked at very basic questions of, I have some function, I want to estimate the influence, I want to look at upper bounds and lower bounds on the influence of any given variable on a function, and I want to use it to design better learning algorithms. Intuitively, if a few variables can control the output of the function, then that function must have a certain special structure, and that can be exploited. Conversely, if no variable has much influence on the function, it has a different structure, and then that can be exploited in some way. So there's been some very nice results in the theory of machine learning, linking influence of variables and functions to how you can learn such functions. We won't talk about that here today. I just want to give you some context for where this question comes from. In the world of statistics, I guess, so we're getting now closer to data science, right? If we talk about the world of statistics, these kinds of questions, of course, get asked all the time. Again, there should be no surprise to any of you that people are looking at this question. So a simple example is take linear regression, right? So in linear regression, you're trying to model some phenomenon, right? And you expect that your y is some, your y vector of your responses is some function of your x matrix of responses times some linear function, and maybe there's some noise here, right? And the goal of linear regression is to figure out what this is. You're given x, y pairs, and you want to figure out what this thing is, right? It's a standard linear regression problem. So you can do this. You can figure out what your regression model looks like, and then what happens is you can say, well, now that I've built a regression model, so now I know that my output depends on these variables in this way. What is the influence of individual variables, right? And the most immediate thing you can say is, well, if I have y is equal to sigma beta I xi, right, plus some noise, then it seems that the relative value of the coefficients should give me some sense of relative influence, right? If the coefficient is bigger, then a small change here will lead to a larger change here, right? Because the derivative of y with respect to any xi is equal to beta I. Right? So this is, of course, if you knew what f was, you could just do direct differentiation and try to figure this out. Now this is a bit more complicated than it looks, because variables have different units, they have different ways of being measured, things can change. So just looking blindly at the actual value may not actually tell you really what the relative importance is, but it gives you some clue. Right? So you can see even in this simple setting that it's relatively easy, you can have some handle on the influence exerted by individual variables on the output of a function just by looking at the function itself. The challenge, of course, is what to do when you don't know what this is. And all you have is a way of sort of evaluating it. Okay? So does this sort of basic setup make sense? The question we're asking today? For those who came in late, I should mention I just did a little switcheroo. The topic I promised to talk about today, I'm actually going to push it towards the end, and I changed up the order a little bit because I felt this would be both a good break from the discussion on fairness and also something that has a more general interest to all of you, which is accountability. So, okay, so this is the setup. This is some basic ideas, and now I want to start talking about how people have begun to start thinking about this in the context of machine learning. Okay? All right. So the first work on this was by Leo Bremen, who is known for many nice ideas in statistics, bagging, and being one of them, and random forests being another one of them. So he wrote this very influential paper on random forests, which laid out sort of the notion and brought together some different ideas. He didn't invent the idea, but he brought together many important ideas in the area. And apparently he has a copyright on the term random forest, which is a little funny. So I'm using this hopefully without violating any copyright laws. So. Huh? He's got some kind of legal ownership of the name. At least in India. Okay, that's good. So then, as long as the video doesn't go anywhere else, I'll be fine. So. So again, we've heard a little bit. We heard about decision trees, of course, and we talked a little bit about random forests yesterday. The specific details of random forests actually will not matter for this discussion. Suffice it to say, we've talked of decision tree being a single tree, but in the random forest you may have a whole collection of trees, each generated randomly through some process, maybe by randomly choosing which attribute you use to split on and so on. And then once you get this collection of attributes, a collection of trees, they essentially vote. So the label for a point is basically the majority label from tree 1, tree 2, up to whatever number of trees there are. So all the trees vote for what they think the right label for this point is, and this label gets a majority one, or the plurality if there are more than 2. Okay? All right. So in this paper, after he spent a lot of time talking about things to do with random forests, he asked this sort of interesting question, where he said, and I'm looking at the paper right here, in some applications, and in particular medical applications, and this is again a theme that comes up often, it's critical to understand the interaction of variables that's providing the predictive accuracy. Okay? So you want to understand the interaction of the variables, which variables are driving the predictive power of the function. Right? So in general, of course, this is some arbitrary function, but in the case of machine learning, this is my prediction, my classifier. And you want to know which variables are controlling it. Okay. So what is his idea? So his idea was the following. It's a very natural idea. And here's what he said. Suppose we believe a variable is not very important to making the decision. That somehow the model is not really using information from that variable. Okay? Then we should be able to test for this fact as a kind of null hypothesis by scrambling the values of that variable. Okay, so what does that mean? So what that means is that, so let's say I have a data set, and you can think of this as, again, as a table. You have the items, and these are the features. Okay? And these are the features, of course. Where's my thing gone? These are the features you can think of as the variables. So we'll call them x1 to xn. So there's not these are just the features there. And you want to know any particular feature, what influences has on the outcome. The claim is that if this feature is having no influence on the outcome, then it's as if it's not even looking at it. And if it's not looking at it, then the values you put in there shouldn't matter. And if the values you put in there shouldn't matter, then I should be able to scramble them up, get a new data set, and get the same outcome. In other words, given D, I'm going to transform it to some D prime. Okay? in which everything else stays the same, but this column, I apply some permutation on it. Because your model, syntactically your model takes so many parameters, right? There's a type check problem, right? I mean, if I have a function of two variables, I remove one variable, I can't feed that thing into the function.
Yeah, I'm not saying just not remove, make them zero, or make them some constant value, same value for all.
But alternate value is a different thing altogether. I mean, this is basically, think of this like permutation testing. So if you're doing sort of Fisher-style permutation testing, what you're trying to say is, what you really want to do is run this permutation test multiple times and see if there's any effect on the result of doing this. So this is basically a null hypothesis test, right? Disguised in this. Yeah.
If you make them giving a constant value
Yeah.
instead of just permuting it,
Yeah.
then probably that would be a better test. Just a permutation. Why permutation? You can somehow articulate it.
Yeah, so I mean, the same kind of objection, I think, could be raised about the original idea of permutation testing itself. So Fisher's idea of permutation testing. Because this is what he said. He said, okay, take the data set, just sort of scramble things up and see what happens. What you're trying to, what the idea here is the following, that you're trying to,
See, the basic idea of permutation testing in this case when you scramble is to actually see whether there is a correlation between different attributes.
no. The idea of permutation testing is to generate a sampling distribution. So you can evaluate p-value. So you can do p-value testing, right? So, so that's why you, okay, so let me back up a second, right? So let's go back to the basic. So the basic idea of permutation testing, right, this goes back to Ronald Fisher, right, in the early 1900s, is that you have a null hypothesis, right? Or you have some measurement of the data. So you have some data, you apply some function and you get some number. And you want to know, is this number significant or is it just noise? So for example, you cluster a data set, you get some clusters. Are these clusters real clusters, or they're just some noise that the algorithm is struggling and finding some patterns in? Is there a real pattern or not? And the way you set this up in a statistical framework is to say, well, let the null hypothesis be that there in fact is no pattern, there's no signal. This number is not significant that I've just computed. And let me try and disprove the null hypothesis. And so I say, if in fact this value were just from the null hypothesis, then I can try and essentially sample from an induced distribution over the data and see how common this item is, or how common items like this are, okay? And if this item is very unusual, this value I get is very unusual, that doesn't often show up in my sampling distribution that I simulate over the data, then I feel more confident that this is a real thing, that's rare. This is the basis of all p-value testing, right? You say, okay, look, the p-value of, the likelihood of this arising from this null distribution is very small, so therefore it's significant. Now, there's a lot of problems with p-value testing, which I won't get into, but this is the basic idea of doing that, okay? So then in order to do that, you have to construct some distribution that the data appears to be coming from in order to do this p-value testing. And so there are many ways you can construct this null distribution, but you have to do that distributional thing. And that's what you're doing here. You're basically choosing random permutations of this column to create a distribution over data sets in which you can now evaluate the value of this particular data set. If you just set them all to one value, you haven't created a distribution. There is no way of testing significance. Because it may be that you made them all to 0 and somehow the value changes a lot just by accident. Fine, but okay, but random values is different. Giving it a fixed value is one thing.
That's what. The question now is, there you give random value, but there you're giving only permutation.
So I think there's a reasonable discussion you can have about when you should use a permutation of the data.
There is some specific reason, or
This is something I'm not entirely sure of that. I think, and I've seen, and we'll talk about this, people do one or the other. I mean, it's not as if, there's a, yeah, so one reason to do permutation testing is that you are not imputing anything to the data that isn't already there. So in other words, if I say take random values, from where? What range? You'll say, okay, look at the min and the max and take values in the range. Then you say, okay, but what distribution should I pick? Well, I have to pick a distribution. If I just do permutation testing, I am not adding anything to the data that isn't already there. If some value is repeated 5 times in my data, it'll be repeated 5 times in my permutation. So it's somehow a very conservative assumption about what the data is telling me. And that's one rationale for permutation testing. But I think it's perfectly reasonable to say, oh, we could impose a distribution on this and sample from that as well, or some uniform distribution or something like that. Right? Even if you're a Bayesian, you might have a prior on this. So but the basic idea is build some kind of distribution and get a new data set by sampling from that distribution. Okay? And so you could imagine getting a D prime, and so D prime 1, 2, 3 up to D prime n. You can get a whole bunch of them, right? And so now you can say, okay, I will evaluate the function on the original data, so I get some number, and on all these variations here. And I can take the average or do whatever. And the question now is, has the function value changed? Is there a significant shift in the function value? So in this case, let's say I just take this 2, I take the second one here, and I say, okay, let's compute delta I is equal to f of d minus f of d prime I. And I'm going to put d prime I here just to denote that variable xi was the one I fiddled with. Okay? And you get this 1 for every I. And now you can say, okay, if delta I is small, then the influence is small. If delta I is big, then the influence is big. And in general, you could think of sorting these things, right? You could just sort them and take the variable that has the biggest delta is the variable that has the biggest influence. Okay? So again, the intuition here is that you want to perturb the data and see if perturbations with this variable change things a lot. And in the extreme case, if the function never used this variable at all, then of course no change is going to happen. So that's the extreme case. So it'll be 0. It'll have no influence. Of course, that might not always work. It'll have a little bit of influence.
So if we do the permutation, then there will be many combinations.
Yes.
So how to select this?
What you would do in practice is you just sample from them. You take a sample of them and take the average. So take a sample of a bunch of permutations, compute the average of those values, and then look at the difference. So Brayman's paper is very limited on details. His writing style is more like a little conversation over coffee with the reader. So he's like, oh, I did this, I did that. He doesn't really get into too many details about what, and he sort of says, oh, this needs more investigation. So he just leaves it at that. It's a little like half a page in a paper, but it's and he gives some numbers, more than half a page, like 2 pages. But he gives one example and he shows how these things work. But this is, in many ways, this sort of modern start of the idea of how to probe a classifier or some kind of model to detect influence of variables. Okay? All right. Question so far?
Any specific algorithm you use for classifier?
Any specific?
Algorithm.
Oh, he was using decision trees. Yeah, a random forest actually. So and also, so that's the thing, right? In a decision tree, it's relatively easy to see what variables are influencing the outcome, right? You can look at essentially things like, well, it's not completely obvious, but something like you look at a subtree that is relatively homogeneous, then the decision at the root of that subtree is going to have a huge influence. That's the one that's going to tell you, okay, go this way. Or rather, if you have a variable whose outcomes are relatively homogeneous, like if you have the answer to this question, this goes to 1, this goes to 0, then okay, so now this variable has had some influence in the final decision. The higher it up it is, the more the influence it's going to have. So you can do that for a single decision tree. For a random forest though, because you have this combination, this ensemble of trees and they're all voting, it's not as clear to tell what's going on. What's kind of funny is that in this paper, he sort of, and in papers like this, they sort of say, well, decision trees are okay, but random forests are very hard to understand. And I don't know what they would think of neural nets now, which are, compared to, nowadays people say, well, random forests are easy compared to neural nets. So the perspective is very different now.
And maybe because of decision trees, he has used the permutation.
Um,
For a single variable, it makes decisions, like variable range from this to this. And if you put the constant, so the algorithm will not be able to make the decision. So maybe that's why he has used it.
It's possible. because the decision tree works on single variables at a time and it makes sense to do that. I think it's also because he's looking for the effect of a single variable. And this brings up an interesting point, right? So Bremen's approach is a nice approach. It sets out this basic principle of perturbation as a way of gaining an understanding of influence. And this idea actually is not going to change. We're going to keep using this idea over and over again, right? But there are some limitations to Bremen's idea. Any thoughts on what those limitations might be? So there's the things it might not be able to pick up on. That's the point.
In continuous average case, there might be some some specific values of xi where this is very large and on average it is 0 or lower. For example,
Right.
in the decision tree, they say if someone is a billionaire, then do this, otherwise do that.
Mm-hmm.
And because when you keep the billionaire on average, the difference of the value will be 0.
Mm-hmm.
But there it has influence. There are cases where it has a lot of influence.
So then the question is, you have to then, right, so then this is always the dilemma with using the average. You have to say, well, on average the influence is small, but there's this outlier which is very big, then do I want to look at average influence or not? Because then you could say, well, I don't look at average influence, I look at the median influence. Then you might be able to pick up on that or not. So there are ways in which you could try to address the problem with averaging by changing the way you define this quantity here. So that would still work within Bremen's framework, but you would have to tweak it a little bit. So the other question then is, are there things where the framework itself cannot really handle it, not as stated?
So one way is like I was saying that if we remove the variable, so what we can try, like if we can remove one variable, can construct one tree, and then we have to do this for all the variables, and then find out the best, and then find out the distance between best to all the.
I see.
Again, the thing is, what you observe that when you do anything except permutation, it's like sampling with replacement, and then that's
No, we are not using any of this.
He's going to delete it altogether and build a brand new tree.
And then we have to find out the distance from the best to all the. And in the case where the distance is highest, that will be the significant, most significant.
So the problem though, I mean, I think this is generally speaking, I think this is a good idea to try and explore how different variables might affect the model creation process. But remember that in this setting, we fixed the model. The model is already baked in. You can't change it. I mean, what you're saying will work to sort of explore more generally what kind of models you might see if you delete different variables. But here, in some sense, the model is fixed. It's hardwired. Someone gave it to us or something, right? So all we have the ability to do is probe it now, right? And even if you can change the model, you want to know how good this particular model is before you start messing with it. So we want to keep the model fixed in the setting, right?
But let's see, in this random forest, you have multiple trees. So we can obviously see what he is saying. In one of the trees, the influence is like this, and another tree is so like extreme cases.
But the trees will also change if you build a new model, right?
There are multiple random decisions. So it's a random forest.
Yeah.
What is the effect on an individual or a group, subset of trees in the random forest? So just your idea of it.
Yeah. I mean, so you could. Problem is, I don't know. Every iteration of this run, you'll get multiple different trees. So then I'm not sure how you compare them. Right. So I'll take one variable out. I'll run my model. I get 5 trees.
The model is already big there.
So it's fixed. Okay. So now I delete the variable. How do I input it into the model now?
You don't delete the variable, you set it to constant value, 0 value, or whatever the minimum value.
Yeah. And you run it.
And then different just see what is the influence of it.
I see. So what you're saying is that so in this setting you could actually not just look at the overall influence of the variable on the model, you could look at the influence on individual trees in the model as well. Yes, absolutely. Yep, you could do that as well, right? So that's something that would work. So as you can see, that things. So we still haven't got to the where could things go wrong? And one place where things could go wrong is if you have a joint influence, where 2 variables don't individually affect the outcome, but they affect it together. Right? So for example, let's see, one example I had, which I thought was nice, which I kind of wrote down. I don't have it. Okay. Thought I'd written it down here. Yeah, so, and this relates to this point about the billionaire thing, right? So one variable is influential only when another variable appears, and otherwise not. Right? So these two things have to be looked at in conjunction, especially in medical diagnosis. This often happens, right? So, you have a headache, okay, whatever. Your nose is running, okay, whatever. But if you put them together, I don't know, maybe something worse is happening. I'm not a doctor, so I don't know what that could be. But you could imagine that a combination of symptoms is going to be more significant than any one of the symptoms by themselves, which could be much more innocuous. In which case, if you're building some diagnostic tool, you would like to know that it's looking at these kinds of correlated patterns and that it's able to pick them up. But this method will not give that to you because it's only looking at one variable at a time, right? Now, of course, in some sense, there's nothing really stopping you from extending this idea, right? And so one of the next papers we're going to look at is a paper that basically does precisely that. So, let me see. So this is a much more recent paper. So it's, in some senses, it's surprising it took this long to kind of figure out some of these things. But people have been slowly exploring in the realm of binary classification what kind of influence measures you could use to probe the effect of a classifier. And so this other paper looked at two things. So, So they wanted to understand two kinds of influences that might show up that the basic approach would not capture. The first thing that they wanted to look at was joint influence. Right? And so what that means is that they wanted to tell whether, again, you have some function of x1 through xn, and that somehow, x3 and x5 jointly affect the outcome. Okay. And conceptually, there's really nothing different between this and what I just told you. This should be easy to do, right? Which is why I'm a little surprised it took so long to figure this out. So, how do you do it? Yep. Just so now it's the same as before, right? So you just build a table. You have x3 and you have x5, right? Treat them as a single thing. So really treat them as one thing like this. I'm ignoring the thing that's in the middle, of course. Right? And now when you run your permutation, permute these blobs together. But not separately. In fact, you could even do more, right? You could actually permute them individually and then you can compute a delta 3, just like before. You can compute a delta 5, just like before. Huh? No, yes, so one second. And then you can compute what I just said, which is delta 3, 5. Right? And in fact, if you're looking for a joint influence that doesn't show up in the individual influences, you could see that maybe these two numbers are small and this number is big. Right? So you can generalize this idea of permutation-based perturbation of the inputs to handle more general subsets like this. Well, this would not detect it then. Then you have to look for x1 and x3.
In that, you want to see if x1 and x3 are jointly affecting and x3 and x5 are jointly affecting.
Yeah.
And you want to find out what's the influence of each attribute on the function. Then how can we conclude for that?
So if in fact the function has the form where x1 and x3 influence it, and x3 and x5 jointly influence it, then this test will, if you knew this, you could test for it. You could say, okay, what are these numbers? They look big. But then the answer I'm giving is not what is the influence of x1? It's more like here is the joint influence, or here's the significance of the influence of x1 and x3. I'm not going to give you an answer for a single variable. I'm only going to give you the group answer. Because there is no separate answer to give. Does that, I don't know if that answers your question.
So this process is used for one of the situations where we want to remove some attributes.
You want to remove some?
We want to remove some attributes because there are more number of attributes. We can use this process for that condition also.
Why do you want, you mean like dimensional reduction? Like dimensionality reduction? Like, why do you want to remove those attributes?
So if any attribute is affecting very less, so why?
So they're non-significant in some sense. So who said non-significant? Okay. So non-significant attributes, what you're saying. I see. So you're saying, could you use this to remove things as well? Okay. Yeah, you could. I mean, so again, there's this whole area of what is feature selection, finding out features that are important and features that are unimportant. And yes, you could imagine this in reverse as being a way of saying, find the things that are very small single influence and remove them. But you're right that if now I'm only reporting joint influence, I can't remove anything. Like if x1, x3 are influential, x3 and x5 are influential, or not influential. Okay, suppose you have a situation where x1 and x3 are influential, x3 and x5 are not. So this is and this isn't. There's really nothing you can remove here yet. So we don't yet know what to do. So that's a slightly different problem, right? You can use this to do that, but it's a different problem to the one we're trying to look at here. But it is definitely connected. So I mean, does that answer your question? Sort of, maybe. Okay. All right. Good. Yeah, that's a good point. So you can do that. So handling joint influence is kind of easy. So we know single influence is easy. Handling joint influence is not as easy, but it's still relatively easy. There's one minor, well, not minor, but there's one problem with this joint influence thing. You have to know that you're looking for the joint influence of x3 and x5. And if you don't, then you have to search for which variables have joint influence. And there are many, many more joint influences you could be looking for, exponentially many, than single influences. So there's a whole problem how to search for these influence things. And that's another thing that, we might talk about a little later or might not, but that's one issue here.
Now suppose like x3 and x5 are having maximum impact on the output.
Yeah, together. Okay.
Together. And we have done the permutation.
Yeah.
So definitely they will going to affect the outcome.
Right. So that delta will be very big. Yes. Yes. So what's your question?
So I'm confused.
Okay. Is your confusion in the form of a question or in the form of you?
We are not destroying our data set. I'm thinking in that
When we're not touching the data. We're just creating auxiliary data sets to test out the influence of something. We're not just changing the data.
Why not finding out a joint probability over the outcome method attributes?
Okay, so say that in a more precise way. You want to find what?
Joint probability, whether they are independent or dependent attributes on the outcome.
So you want to check. Good. So what you're asking is right, is the outcome this is essentially a way of testing that. This is permutation testing is doing essentially that, right?
No, with the existing, what you said, without the permutation.
How would you do it?
So taking out, extracting those values and checking with the outcome.
But how? How will you check independence? You'd have to plug in new values and see what happened, right? I mean, in order to check if this is true, you have to basically show that the probability of a particular outcome and x3 is equal to something and x5 is equal to something is equal to the probability that f is equal to something times the probability that x3 is something and x5 is something, right? So you have to check this independence, right? How are you going to check this now? You've got to evaluate these probabilities for all values. Right? I mean, I'm not saying you can't try to do that, but I'm saying that you have to solve that problem. It's not that simple. Right? And this is essentially a way of trying to get at that. Because remember, the biggest problem we're facing is that we don't know anything about F. If we knew things about F, we could probably be a lot smarter. For example, in the case of linear regression, there are many things you can do to try and figure out influence. There's lots of more clever techniques you can do here. But that's because you have access to the model itself. You have some explicit expression of how the model depends on its parameters. You don't have that here. And if you want to think about a neural network, right? 150 million node neural network. No, I mean, some of these are. Right? You take some input and something happens. What do you do now? How am I supposed to analyze things like this? That's the problem.
So actually you are trying to approximate the function f through permutation.
I would like to agree with you, but I can't because I'm not really, that's too much for me. I don't want to do that much work. I don't want to figure out what f is. That's too hard, right? I'm asking a much more, in my mind, easier question, which is merely to figure out a rank ordering of variables, not even a quantitative, just a rank ordering of which variable has the most influence, right? And I want to be able to do this without knowing f, because if I have to know f to do this, that's too much work for me. That's a sufficient condition, but is it necessary? And this argument here that's not necessary. You can get away without it. Okay? Good. Okay, so joint influence is one thing that we can easily do with a slight modification of this. But there's something more interesting that you can do, which they observe, which is kind of cute. And let me describe that to you. What they want to know is, trying to find the right phrasing for this. So what we can do is do something a bit more conditional as well. And this will get us to a more sort of larger, a more general way of framing this problem of influence testing. So one thing that the Henelius paper that I've linked to proposes, along with the joint influence idea, is the following idea. Suppose we want to determine if attributes A1, A2 are independent, conditioned on the outcome. Okay? So think of this as a more general problem, right? So we talked about probing the function to figure out individual or joint influence of variables on the output. But now we're asking something a little bit more involved. We're saying, okay, now I'd like to understand how different variables interact with each other. Okay? And so one question I might like to ask is, can we measure if two variables are independent for any given outcome? Right? So they have an independent effect on us. They don't seem to react under as conditional. And the way to think about that is saying, okay, if we want to look at the behavior of attributes conditioned on an outcome, right? Then think of our data table as before. So we have remember we had our data and we had the features, and we broke up the features into, we took a feature and permuted it to get a new data set. Now let's do things a little differently. Let's sort of reorder our rows so that the outcome is the partitioned by outcome. So this is f is equal to 1, this f is equal to 2, and so on. Right? So whatever number of outcomes you have, it's partitioned by that. And suppose what we do now is only repermute an attribute inside a group, but not outside. So we do one permutation here, one permutation here, one permutation here, but we don't let values go from here to here to here to here. Okay? So of course what this is doing is basically by fixing the value of the outcome, you're conditioning on the outcome. Right? So you basically say, okay, for a fixed value of f, let's do this permutation. suppose there is no change in the resulting, so you can, again, you do this, you get a new data set. So I do this, I get one data set, I get another one, right? As before. And again, I can run my influence tester to say, okay, what is the value of the function of this new data set? Okay? And suppose I don't get any difference. So I permuted this locally here, and I did not get any change in the behavior of the function with respect to this attribute xi. What does this mean? What it essentially means is that it doesn't mean that this attribute is unimportant, because we're not actually permuting over the entire set. It could change the values quite dramatically as you do the other side. We don't know that. What it does say, though, is that this attribute is independent of the other attributes conditioned on the outcome. Let me write that down. That's going to be an important point. So in other words, if you do this permutation testing and there's no change, so we'll call it this delta prime, I is small, right? Where prime denotes the sort of modified version of testing, then xi is independent of other variables conditioned on f.
In short, this particular feature is like high correlation with the weight.
Is that what I said?
No, not say that, but this time you
Does that follow from what I said? No, it might, but I'm not sure why that is true.
you are permuting something and something has some value.
Yeah.
And changing that for a particular label, some changes here do not change the label. There's a high correlation.
Or low correlation. Well, not high. It's not changing the output, right? I'm not even sure it has low correlation, but if anything, it's definitely not high. Because I'm saying that very little change happens.
No change happens.
No change happens. In other words, right? Okay. So one way to think about this is this, right? Suppose that, and we talked about this in the context of naive Bayes, right? Suppose that conditioned on the outcome. So the probability of all the different variables conditioned on the outcome could be written as a product of the individual variables conditioned on the outcome. Okay? Suppose this was the case, right? That the data was generated by a process that looked like that, this independence assumption. Then you can see why permuting this will not make a difference. Because if the model is saying, look, all I care about individually what these things look like, I don't care about their interactions with each other, then permuting this makes no difference to what the model is going to do. It's just looking at the values are the same. And this is again where the permutation helps, because I can say the values are exactly the same. Nothing has changed. And so it's going to give the same answer. So what you're able to do with this modified kind of permutation testing, where you've changed the way in which you permute the data, is basically allowing you to conclude that this variable is independent of its other variables conditioned on f. So you have this kind of conditional independence here. So what the Hennelius paper is basically saying is that building on the idea of Bremen, this idea of random permutations, you can think more generally about how to do the permutation, either in blocks or in this stratified model. And by doing so, you can probe at other interaction possibilities of the data. Okay? And essentially what we're seeing is that, so if you remember I talked about the null hypothesis, right? So there's a null hypothesis that the variable has no influence on the outcome, and you want to check this hypothesis, right? What's really happening is that the act of choosing how to permute is equivalent to building a certain mental probabilistic model about how the data is being generated, right? The act of permuting this variable and checking for no change is also the act of saying this variable has no effect on the outcome. The act of grouping these things together And then doing the chain, say, okay, maybe these don't have any effect on the outcome. And similarly here. So there's a kind of a duality or a mapping in some sense, or at least an informal mapping between how you do the permutation and what kind of model you expect the data to be coming from. And so the test is then used to validate the assumption about the model. And that's how we're trying to probe these models. Right? We're trying to probe them by saying, okay, let's run this test. If in fact this kind of dependency structure existed, this test should reveal something. Either it does or it doesn't, and that tells us something about the model. Okay? So what this paper then tries to do, using these tools, is to say, okay, you gave me this model, it takes all this data, all these features as input. Let me throw some diagnostics at this model to understand all the different possible interesting interactions that might be happening in the data. So for example, it says, okay, can you, let's see, sorry. So can you do things like, say, take the model, take the data, and search over the space of features to find large groupings that maybe don't affect the output, or find groupings that actually do affect the output a lot. Can you search for such groupings? Can you search for how big they might be, how small they may be, and so on? So the output, so the idea here is to take your model and your data and put them into this gigantic analyzer. Think of this like a gigantic scope, which then spits out collections of variables that have influence of different kinds. And this works for any model, right? So you could build any model tomorrow, put it into such a system, and see what it produces for you. And this gives you a lens on how the model looks. It gives you an idea of accountability of influence estimation.
Given that particular data. You should be running this from time and again when you have more data.
Right, right. You're using, so the data, so the data is being used as a probe to the model. The model could be built with something else entirely, right? The model has already been built from some data somewhere. You have some data set, you can try it. You can definitely try it in other data sets. The hope is that through this random permutation testing, you get some sense of overall data sets, what's going on. But the more you try, the better it's going to be, right? And so this little toolbox is what I think is a very useful toolbox to have for anyone who does anything with data mining. So try to understand, a way of understanding what the model is doing. Okay? And in a little bit, I'll sort of briefly mention how we were using this in one of our papers, this idea, but also being able to analyze things like take a deep learning system and analyze what it's doing. And that's one of the attractions of this approach. Okay? So that's one of the takeaways I think, from the things I'm going to talk about now, is I want you to take away from is this idea of having this toolbox that can scope out what's happening inside a classifier or any model that you build. Okay? All right. Is sort of some work that we had done in this space. And we had, so let me give you a bit of the history of where we came from, so that provides some helpful context for how it fit into this larger framework. So if you recall, we had talked about a couple of days ago this idea of disparate impact and this information theoretic approach to testing whether a data set could potentially have bias in it, and then a way to repair a data set by merging distributions together in some way. so as to remove bias in the data. Right? The problem with that approach, one of the weaknesses, was that it all happened at training time. So in other words, you have data, you're trying to build a model, right? And you want to modify the data prior to building the model, because you don't want the model to absorb biases in the data. Okay, that's good. And even if I don't have access to the model, that's a helpful thing to do. But if someone tomorrow comes to me and says, look, my model's already built, I'm not going to change it now, none of what we said before is going to be useful, right? So in that case, if we want to see if there's any bias in the system, we can't do these kinds of tricks anymore. We can't say, look, just train on this good data that I'm going to give you, the sanitized data. We can't even say build a fairness-aware classifier like yesterday. We have no choice. So the modeling is done. All we have is this black box function now. So if you want to check if there's sort of bias in the system now, all we have the ability to do is probe it with some test data and see the outcomes. And now you begin to see the connection to the problem of influence estimation. So our goal originally was still about bias, but as we looked at this, we realized that the connection, there was a larger connection to this general problem of influence estimation. And what's interesting, what's interesting about this framework coming from fairness is that it now forces you to try and test out influence structures that these methods cannot pick up. Okay? So what I'm going to do now is talk about something that we've seen many times before, which is this. So all the influences we talked about, we will generally deem as direct influence. How does the feature affect the outcome? Right? So I have some function. If I knew what the function was, it's like f is equal to something times x5. Okay, x5 is directly affecting the outcome. Right? So suppose we wanted to run, suppose we wanted to use these direct influence techniques to detect an issue of bias. So for example, let's say there's some procedure for giving out loans, right? And people are applying to this procedure and they're getting yes and no answers. This has been built, right? Someone's built a system and we're trying to investigate what it does. And we want to know if it's biased. So we might say, okay, let's apply these direct influence techniques. Let's see, okay, we will test for what is the influence of, caste, marital status, gender, other things, religion, things that we might think would be things we may not want the system to be discriminating based on. And now the system checks out and says, oh, in fact, I will write down the influence, the deltas for all these things, they're all really small. There's very little change in the outcome based on this explicit variable. In fact, when they admit to you later, we actually don't even use these variables. They're not even there in our system, which is why our numbers are so small. You can do what you want, it's not going to make a difference. What you'd like to be able to say is, okay, good, we're done. We're happy here, we can go away, this is a good system. Can we do that? I mean, the clue is already there in what I wrote down, but can we be satisfied that the system is providing fair decision making with respect to these variables based on this testing we just did? They're not? Yeah. So you're satisfied at that point? You're concerned that there's a trick here, but you want to say yes. Yeah? So we talked about proxy variables, right? We said that the encoding, so a lot of people, for example, will drop their last name, right? And why do they do it? Because you know that from someone's last name, you can infer certain things about their caste, right? And so even if you don't collect these variables, there could be other variables in the system that you aren't looking for because they're not these obvious variables. where they are causing some influence in the outcome, or rather this variable is influencing the decision indirectly through the other variables. Right? So this one of the most stark examples of this, I don't know, did I talk about redlining already? Did I mention redlining before? No, okay. I don't even have a red pen, it would be nice, but okay. So the story goes something like this. So there's this term called redlining, which relates to all this problem. And this goes back to the 1930s or so. This was in Chicago. And these banks were giving out loans. Right? And there were explicit prohibitions against discriminating against minorities, and against African Americans, based on, just based on their race. But the banks didn't want to give loans to certain people. So they said, okay, well, we're not discriminating based on race. We're going to look at where you live, your PIN code essentially, and based on that, we'll decide whether to give you a loan or not. And they would literally on a map, they had these maps out there, we discovered at the time, physical maps, no Google Maps then. They would actually draw with a red pen. Imagine this is a red pen. They would draw sort of mark boundaries. So this is some zip code here, and there's another one here. They'll say, okay, if you're from this, we won't give you a loan. If you're from these other ones, we'll give you loans. Now, not coincidentally, because people used to live in very segregated neighborhoods, these neighborhoods are mostly black, and these were mostly white. So the race attribute via the proxy variable of zip code, which is basically a PIN code, had an effect on the outcome. But there was no direct effect, because that would have been illegal. And of course, this is the basis for all the things we've been talking about with regard to fairness, are these indirect influences. And so the problem is, if you say to a system, okay, I'm going to test to see the influence of race, I'm going to permute the race variable, it's not even using it. So of course it will look like race has no effect on the outcome. But it is having an effect through a proxy. And if you knew that this was a proxy, you could test for the influence of this. And you could say, okay, there seems to be a problem here. And this is not even this is from the 1930s. There's an example from 2 years ago where car dealerships, again in Chicago, are being accused, and right now are being accused of bad lending practices to minorities. In other words, they would give them loans, but the loans would be much higher rates, and they have more points, and all kinds of bad things. And the car dealership said, how can this be? We don't even collect this information. Because everyone's yelling at us about being biased, we never collected any race information. There is no way we could be biased. And the government board that supervises these entities and is suing them basically said, no, we built an algorithm to reconstruct this from other information, and based on that reconstructed data, there's a problem. Now, you can argue whether this makes sense or not, because it's only a reconstruction, it's not ground truth, right? We don't know if this really is a race of the individual or not. Nevertheless, this is another example, a more recent example of how potentially indirect influences can creep into a decision-making process. And you still need to know what they are. And this approach is not going to get you there, whether jointly or whatever, because these variables are not explicitly being used. They're being used through their other influence. And so the question then is, what do you do in that case? How might you go about identifying the influence when the influence is indirect? So in some sense, at this point, you already have enough information to reconstruct the rest of this paper. In the past number of days, I have told you enough information to solve this problem right now. I mean, that's how we solved it. So, what should you do? Can we solve this problem right now in class? It'll make me look bad because I wrote this paper on this and I spent some time, but that's okay. I don't mind. As long as you get the answer, I'm happy. What should you do? So again, the problem is to identify or quantify in some way the influence of variables that may have an indirect effect on the outcome through some proxy. Yeah.
Like biasness means we are biased to some suppose some group of persons.
Yes.
Okay. And second thing will be priority. Like in India, there are many government policies in which we have to be biased so that they can grow up. Like if they are poor, so we have to be biased so that they can also come to a certain level.
I see. So there are policies that give preferences to some groups to help them. Yeah.
So is there any such policies in US as well? Because
No.
if this is the policy, then there is a biasness.
No, we're not allowed to have them. There's this whole thing about how the U.S. Constitution does not allow for this kind of thing, and the Indian Constitution does allow for it, because of subtle wording differences in the way statements about equality are articulated. So, for example, one university, I think it was Michigan, tried to use race as a feature to help admit students from minority groups to improve diversity. And then they were sued. And this case went to the Supreme Court said, no, you can't do that. But they didn't say you can't use race. They said you can include race information as part of a larger collection of attributes that are used to determine admission, but you can't use it directly. So it's kind of weird that their decision left some ambiguity about how to use it. And so ever since then, there have been these court cases that keep coming up, where like, oh, well, one happened in University of Texas last year, and that went up to Supreme Court, and that was, so far, the courts have said, as long as you're careful about how you use this information, you're allowed to use some amount of demographic information to help you get a better student body or whatever, but you can't use it directly. Yeah.
Now when the admissions we have, in IIMs, for example, for the last 3-4 years, they introduced what is known as like diversity marks, in which they give 5% weightage to IIMs.
Yeah.
That's different from any other thing. 5% is given to diversity where they discriminate against engineers.
And said?
Discriminate against engineers.
I take personal offense to that. But then again, I wouldn't be going to IIM anyway, so I don't really care. So because they have too many engineers going to the IIMs.
Hey, still, decrease, but the Prof was telling us 5 days back that is still the engineers are constitutes of 85% of the class, even after that particular diversity mark.
Yes, so that's an interesting case where I mean, again, this idea, this goal of increasing diversity is also there in US universities. And again, I don't know if it's encoded as precisely as that, but generally it tends not to be, because if you put a precise number, someone can sue you for it. But if you keep it more ambiguous, then it's a bit harder to sue someone for it. So yeah, so things like that have been on the rise.
Whether you see the diversity as fair, being fair, or there's not.
And I think this is a complex issue. And again, the discussion we were supposed to have today, which we're going to have at the end of the course, gets to this.
No, may not be fair as it is.
Well, I mean, it depends. I mean, it's hard to say, right? I mean, again, are you allowed to do reverse discrimination to fix patterns of bias that come from before? To what extent should you say, okay, look, history was bad, we should try to do better, but we can't go back and rewrite history. I mean, so there are different, I think, natural policy positions one can take that are not wrong, they're just different. And I mean, I think as an individual, we can argue about what it is. I don't think as a computer scientist, I have the right answer of what's the right way to do this. There are different choices here. So, yeah. Okay, all right. So again, I will emphasize that the problem here again, and I'm still waiting to hear any ideas about how we might solve this problem, is that you have this indirect influence. And all the ideas we've seen before basically boil down to, okay, do some permutation, do some intervention, intervene in the data, change the data in some way, create these fake data sets based on some distribution, and use it to test influence. Something that we may not be able to do here. Because let me point out one more thing. This attribute may not even be in my set. Right? The attribute I'm worried about may not be one of the xi's. So there's really nothing to permute as such. So the idea we use is an idea that we've seen before. We talked about this a couple of days ago, and not surprisingly, it's from our earlier work, so we decided to use it here as well, is to say, if I want to determine, if I want to really understand the influence of an indirect influence of a variable on the outcome, I have to really remove it from the data. And just doing random permutation of the value is not going to be enough. I have to remove its influence in other variables as well. But where have we seen this before? We've seen this idea before, right? We've seen the idea that you might want to remove the influence of something in something else. We saw this 2 days ago. When did we see it? When we talked about modifying the input data. If you recall, we said we want to eliminate the existence of bias in the data set. So we have some data set and we have some attribute. We want to remove the influence of this, the bias variable from the data set. So you can no longer detect bias. So what did we say precisely? What we said was, what is the thing I said? So basically the idea was, if I have given attributes, there's my sort of, the attribute I'm worried about, which is x, and the rest of the attributes is y, right? If right? Remember this? So we said, okay, in order to modify the input in a systematic way to remove bias, we have this theorem that says that if I can't predict x from y, the outcome will not be biased by x. So the goal is then to somehow remove the ability to predict x from y, and so we said we'll modify the data by merging distributions somehow. So I remove the signal of x and y. Okay? So now let me just change one word in this sentence. And that essentially is our paper. So in other words, the trick was to say, look, the same technique we used to try and remove the effect or the potentially biasing effect of a variable on an outcome could instead be used to remove the influencing effect on the outcome. Right? So if I cannot predict x from y, right, and I build some model to do this, then the outcome cannot be influenced by x at all. So now if I have my data set, so I have my first data set, which is and I have some value on this, and I have some modified data set where I subtract out the influence of x in this manner, right? Now I can actually look at the difference. And this is the measure of the indirect influence of x. I will tell you. So this is the high level idea. Okay? Right? Okay. I can write down single, joint, and indirect. Okay. We've also seen this correlative kind, which is related joint. And then we saw we had Bremon's method. We had this method I talked about by Hernelius, and we have the method that we are using here, which I'll call indirect influence. Right. So Bremon's method handles these two cases. Hernelius' method handles this and handles this. It doesn't handle this. What we do is we handle single, and we handle indirect. We don't handle joint influence, but that in some sense is easy to, oh sorry, made a mistake, okay. So this is the paper, by the way, a peek into the black box paper that I linked on the course website. Okay. And so we don't do anything here, but I will argue that in general, going from here to here, as we said, is not very hard, right? Going from this to this is not hard. What's interesting is is getting all of these influences together. So there is no, as far as I know, technique that gets all these three at the same time. But there's just a way to think about this. And now we will start talking about exactly how this works. I'm wondering if maybe should, sorry, yeah. X is a function of?
Y, Z. Z is some other activity.
Okay.
So in that case, we cannot say that the outcome will not be influenced by X because X is a function of Y and Z. So we can replace the value of X from Y and Z. So individually, Y is not playing any role for the influence of X.
So if my procedure for removing the influence of X works, then it's going to strip out any effect of X from Y and Z. But if X is a function of Y and Z, which means there's always going to be an influence, then my stripping out procedure will destroy all the data essentially. I'll get complete noise. So it'll be very hard to do this. And so my answer will be noise. I'll get a huge gap. It'll say, no, the influence of X is very high. So even if X is not in the data set, but it can be derived from Y and Z in some deterministic way, then the only hope my procedure has is to completely knock out all values of Y and Z, and I will see that effect then. So it will still capture something to do with X, even in that case. That make sense? Sort of. Okay. I'm wondering, is this a good time for? Should we stop or should we? I can go on. It's about 11. It's almost 11:25. Well, we're not ready. We're not sure we're ready yet. So. So when we left off before the break, I was arguing that the problem of indirect influence is a little trickier. And I was arguing that you could potentially use the same idea that we talked about a couple of days ago that was originally framed in the context of bias, but can also be framed in the context of influence in general. The idea being that you, instead of trying to measure the influence directly or to measure the effect directly, you measure it indirectly in terms of a computational procedure, namely this. Right? And so the way I like to think about this is that, you have the variables, well, I was using a different, so you have the variables, I guess, y1 through yk, and you have x, right? And you're trying to figure out the influence of x, the indirect influence of x on the outcome. These are all going into some function f here, right? And so the idea is that somehow you want to subtract out the influence of x in some way, right? So you want to make sure that wherever x has some potential influence, it's kind of blurred out. And so let's look at any particular attribute here, right? So we'll just do it attribute by attribute, right? So you have some attribute yj here. So you have x and you have yj, and you want to subtract out the influence of x on yj. Right? And so we've seen this before, right? So we said, okay, we look at the different values of x, right? And you look at the conditional distributions of y given x equal to x. And so on, right? And the goal, if you remember from what we saw 2 days ago, is that if we can somehow merge these distributions together by changing values, then we can no longer use this data to infer anything about x. Okay? Now, in the work itself, we employed somewhat of a heuristic because we didn't know how to do joint influence removal, so we removed influence one by one on each variable, which may not completely remove the influence of x altogether. But the basic idea was take each variable that you want to, take the variable x whose influence you want to measure, take every other variable, do this procedure of merging distributions that I described 2 days ago to remove the influence of x on this yj and get a new data set. A single new data set. So we're not doing some random permutation testing here. We're doing something deterministic. Right? So this is a little bit different to the perturbation methods that we've seen so far. Okay? Once you have this data set, you can now run it through your model again as before, and then compute the delta as before. Right? And then you can rank order the variables based on the level of influence they appear to have. And what's interesting about this is that if the data set used to train the model, let's say, didn't even have x in it, but you had some other data where you actually had x combined with something else, you could actually remove the influence of x even in a setting where f does not take x as an input at all. So you can do a little, so you don't have to have x be one of the parameters going to the system as long as you have information about how x relates to the other variables that are used. So just a minor detail that makes it kind of nice. And then that's it. So now you can basically take any model, run this procedure on it, and look at the results you get. So here are some things that I think are interesting here. So what we can show is that, one nice theoretical result we can show here relates to the relationship to ANOVA. So you might, I don't know if you're familiar with ANOVA and the F-test. Basically, if you have two Gaussian distributions, right, and now you draw samples, and you want to check if these are the same distribution or not. And this is often a common test that you want to do is check if two distributions are the same or not. And there's this test called the F-test, which allows you to do this. It basically works by, since it knows the Gaussians, it looks at what you'd expect to see in terms of the differences between their variances. Okay, so it's basically a ratio of the between group sample variance and the in-group sample variance. Okay, and so once there's a whole procedure for doing ANOVA. You basically get some number as a result of running this test, and you look at the number is big or small. If the number is small, then these two things are indistinguishable, and if it's big, then they're different from each other. Okay. So one thing you can show is that, or one thing we were able to show is that if you took our procedure, the procedure we used to blur distributions together, and in fact the data came from Gaussians, then what we do is equivalent to doing the F-test. In other words, the F-test will fail on our blurred distributions. So in fact, we will not be able to tell them apart. In fact, we have successfully eliminated the influence of x on these variables. So this statement doesn't hold in general, but at least in the case of, or may not hold in general, but at least in the case of particular kinds of distributions where there are existing statistical tests, the method we use actually gives you what you'd expect as the answer, which is another way of saying that it seems to do the right thing in that case. Okay. So again, the procedure, if you have to summarize it, basically looks like this. Let me see if I actually have the algorithm written out here. If not, I can just do it. Okay. So the procedure basically works like this. So you have a model, and you have variables x1 through xn, and you want to find the influence of xi. So all you do is, for each xj, sort of subtract, in this sense of subtraction, subtract effect of xi, get the new data set and run data set and compare outcome. And that's it. Okay. So what does that give you? So it turns out that you can try this on different data sets. And so I want to tell you about two data sets that I think are kind of interesting. So the work we were doing, one of my colleagues works with a bunch of chemists. Okay? And one of the things the chemists want to do, they So let's see. So basically they're running some kind of, so they have a bunch of chemicals and they run some experiment on it, okay? An actual experiment, not our kind of experiment. They actually run an experiment and they have some outputs of the experiment. And there's a particular kind of crystal structure they're looking for in the output, some kind of ionic crystal. And they want to know if that crystal is present in the output. So they have a whole bunch of compounds. There's something like they had a whole bunch of experiments and they have a bunch of different attributes. There's something like 273 attributes that describe the inputs to the reaction. And there are a lot of experiments you could run this, and they're expensive. Again, these are real experiments with chemicals, so they're not, things on a computer. And so it costs money and time to run these experiments. So what they'd like to do is build a predictor that says, if I give these inputs, will I get this particular crystal I'm looking for or not? They essentially want to build a classifier. So, so they worked with my colleagues. So they had a paper on this, a nice paper in Nature, which is one of these big science journals, which basically showed that they could actually build a machine learning based predictor for predicting, just based on the inputs to the experiment, whether the experiment would be successful or not. It would produce this outcome. It's kind of neat. You're not actually running the experiment, you can do this prediction. And not surprisingly, the way they do it was to use deep learning. So they built some gigantic feed-forward neural network, and then they did it. Okay. So I'm not sure I know how many nodes were there. Oh, I see. So okay. So if it had basically one fully connected hidden layer with 50 nodes in it, and then the outputs there, which means basically think of this as having 50 different parameters controlling what is going on. Okay, so it's a very complex system. And of course, they're chemists, they're scientists, so it's not enough for them to be able to predict whether a collection of chemicals will generate an outcome or not. They would like to know why. In other words, they want to know which variables in their 273 attributes appeared to influence whether a certain crystal was computed or not, was produced or not. Because that might tell them, okay, what the underlying chemistry of the process is, right? Because it's something they didn't understand. So then they came to us, and they said, okay, you have this whole influence estimation thing, can you apply that to this problem? And so we did literally this. We took our method and we applied it to their deep learning system. Okay? And so what you get, and again, the paper has graphs, all kinds of wonderful graphs you can look at and see. But the point is, what you can then produce is a set of features, a list of set of features that say, okay, these features, these 5 or 6 features, seem to influence the deep learning system a lot. And of course, our system knows nothing about chemistry. It just took whatever features based on this appeared to give an interesting outcome. And the result was kind of basically the ground truth here was to go back to the chemist and say, hey, we found these features, tell us what you think. Right? So they're the ground truth. And it turned out that in fact, what we were able to do was identify features, the ones that were most influential according to the system, were in fact ones that they said were chemically very significant. So in some cases, they were not surprised. They said, okay, yeah, of course, we knew that this was going to be an effect. So that's got a good cross-check to make sure we're not finding crazy stuff, that we reinforce things they already know. In some cases, they discovered features, the system discovered features that they didn't expect to see. So they were surprised, but it was not a feature that was just like, this makes no sense. More like, oh, I see this, but I didn't think of this being likely to be important, but I see that that's important. So in other words, we were able to show basically that by using sort of this black box procedure, which knows nothing about the domain, at least in this setting, which is kind of the scientific domain, you are able to infer something about which features appear to be having an influence on the outcome, even indirectly. Okay? And of course, the reason I want to bring this example up is that there is nothing to do with bias, anything over here. And we spent the last number of days talking about fairness and bias. This has nothing to do with that. This is just a probe into your model. Right? And again, to go back to things I've been saying in the beginning of the lecture, this is important, right? that you can, if you have this kind of tool at your disposal, whichever tool you want to use, then you can probe a model that's complicated and try to understand what it's doing. Now that's something worth keeping in mind. Okay. We also, I mean, again, if you look at the paper, we examined this on a number of other data sets. And so typically what will happen is, this is what a graph will look like. So let's see. So what I didn't mention is that you can control the amount of influence subtraction you do of a variable, right? So you can sort of tune it a little bit. There's an extra parameter there. And so once you do that, you can plot this graph that says, you know, how much obscuring do you do? So how much you try to obscure the effect of a variable, and this is accuracy in terms of how well this matches what you had before doing the obscuring. And so for different features, you'll get different curves here. And an ideal curve would be something that looks like this, again, that no matter how much you obscure the feature, well, not ideal. A curve that looks like that will basically say this feature has no effect on the outcome. Okay? A feature that looks like this starts having a huge effect on the outcome as you obscure it more and more. And so basically by looking at all the features, you get graphs that look like this. And then if you look at them from bottom up, these are the features that are most important, and it slowly decreases as you go. So there's a whole series of graphs again in our paper where you can see stuff like this. And there's some data sets for which you get total noise. You get all kind of junk. So it doesn't really, that's telling you that the model is not really something weird is going on. Okay? So think of this as the picture that you can use to inspect the model and decide what's going on. And this is true for, you know, most of these methods. Okay. Any questions? Any questions? Yeah? Okay. Yes?
When we talk about fairness, we started formally giving a value for fair, discrepancy or the other value which we can optimize upon. Here we are not giving any value to influence.
Right.
So is there a common way to define?
That was the question in the back right there. Okay, so someone else asked this exact same question. So the question basically is, this all seems very ad hoc. Is there any formal definition of influence that we can capture here? Implicitly in this discussion, I don't know how formal you want to call it, but the definition of influence is some kind of derivative, because you're basically saying, look at the change in value of the function with the change in the data, right? So the influence function is a derivative. The key thing is, what kind of partial derivative are you taking? Right? So if you think of the data space as this very high dimensional landscape of the data, different kinds of random permutations correspond to different kinds of gradient directions to explore, right? And so this is about as formal as I can state that to be, but it's still not quite there. I think the question about what is a formal definition of influence? In certain domains, it's very, very specific. So for example, in the case of Boolean functions, then your perturbation is basically the 0 to 1 or 1 to 0. And you can say what is the expected value over all of the perturbations. And this can be made precise. In general, this is about as good as it gets. And I think you can come up with specific definitions. You can fix this, you can hardwire this to something or the other. But I think the definition of influence you use will depend a lot on what you're really looking at. So we don't have, so I don't, I think it would be good to have such a definition, at least to make sure we understand how all the different papers are doing things with it. Just like we saw before, okay, this is the definition, these 3 papers look at this definition, these 3 look at that. We're not quite there with this topic yet. We're getting there, but it's still a bit fuzzier. Any other questions? Okay. So, the last paper that I want to talk about is also a paper that came out this year. So all this is very recent. Our paper was, the paper I just described to you, was literally presented at the conference yesterday. So it's actually very, very new stuff. And there's another paper that came out this year, and these other works are also fairly recent. This is all fairly new stuff, so that's why we're still feeling our way around exactly how the story should be told. So this other paper does something that's, in some sense, very related. Right? So it's this paper on what they call quantitative influence. That's the name of the paper. And in some way, what they're doing essentially is very similar to the kind of influence via random perturbation idea that we saw earlier. Okay, and I'm hesitating a little bit here because in my mind they look very, very similar. They're not, particularly different at all. I think the framing of this paper is a little bit more general, which I think is nice to sort of see. So again, the idea is this, and I'll try to draw from this paper is the more general way in which it frames the idea of interventions. So let me see if I can say this the right way. So, okay, hold on. Okay. So once again, we have some model, and we have the input, and let's assume we have some kind of probability distribution of the input. So there's some pi, which is a distribution of the inputs. Okay, and as always, we want to quantify the influence on the model, right? Okay. So hold on one second. Yeah. So we have some kind of model, and we have some kind of estimate that's a function of the model and data. So in other words, if you'd have the model and you have some data, you get some number. In the cases we've seen so far, for example, this was basically how many disagreements do you have with the predictions of the model, right? Or what kind of agreements you have. So you have that number, and you want to estimate the influence of x by looking at its influence on this function, just like before. So again, all this is still pretty much the same. So what they say is that they define what they call an intervention distribution. So let's define this distribution. So given x, we'll define the intervention variable as some variable u, okay? And the new probability, so we had the old probability, which is pi of x for seeing x. The new probability of seeing x and u, right, is going to be written as the original probability of x times some the probability of seeing u. Okay? So think of this like some kind of noise distribution. Okay, but you create this new space over this. And Now we'll say that if we have this space here, this space with this distribution, then this random variable is the projection of the new space onto the old variable here. So in other words, I define a new space augmented with a variable, and then I define the recovery of the old variable as merely the projection. There's a projection operation here. And I will also define this as taking all of x, so x is some vector, right, from 1 to n. So think of taking x1 up to xi minus 1, xi plus 1 up to xn, and then putting ui in its place. So again, we're replacing, so this is a bit different to what we saw before. What we're doing here is we're taking the vector, which you can think of as one data point. We're removing xi, and we're replacing it by some ui, which is some other vector, other coordinate of some other vector. Okay? So this is a difference between the original and this. Okay. So now you can talk about the probability of elements here, and you can do this. So you can now say, what is the probability that some algorithm applied on this is equal to 1. Let's say it's a classifier. So you want to say what's the probability this classifier is equal to 1. And then you can actually sum this up. This is going to be the sum of all the probabilities, x comma u, such that over all x comma u, such that a of x minus I u I is equal to 1. Okay. So the point of doing all of this is to say, I will define some general kind of intervention on my data. Before I was saying my intervention has a particular form to it. I do this kind of random permutation on things, right? And we talked about what might happen if you do something else. This is an example of doing something arbitrary. You have some kind of other way of permuting things. Notice that u is also drawn with the same probability as x. So it's almost like you take another element of the space and you put it in the place of xi. But it's random. It's some random noise, but from the data set. Right? So it's kind of smoothed out. And so once you have that, you can now express this whole idea of what we were talking about earlier a little bit more precisely. Remember, you want to compute some function, I don't know, so this function f, which is maybe the number of misclassification errors or something like that. And so now you can say that the influence of I with respect to f is equal to the function value on x minus the function value on x. Right. And again, this is not very different from what we saw before. It's the same idea. Take it, change it, take the difference and see it. But it's put in a more general framework to make it sort of more rigorous. And now you can say, well, I'll put in different kinds of f's and see what happens. So one thing that's nice in this paper is that they point out correctly that if you choose f, for example, to be a disparate impact measure, what is the skew in your acceptance probabilities for two groups? Then you can ask questions like, what is the sensitivity of a particular attribute towards causing disparate impact? Right? So for example, I'll say f here. So f here is equal to the ratio of the probability that c is equal to 1 given g is equal to 0 divided by the probability that c is equal to 1 given g is equal to 1. This is some function of my data, right? And now I can run it on my original data set and on my modified data set as well. And I can say, okay, what is the difference in the value? So in some sense, what this is going to do then is going to capture the extent to which changing a particular variable affects the disparate impact outcome. And this can actually be very important, right? Because if you have such a tool like this, and you have to go to court and you have to say, oh, look, you have disparate impact, and the company says, well, this was something innocent, we didn't really mean to do this. You could say, well, look, this variable, this problematic variable appears to have a big effect on what kind of impact you're going to have, what kind of disparate impact you're going to have, and it's going to affect your fairness by a huge amount. So again, the connection, so I said that the reason to think about influence comes out of fairness but is more general. Now we can kind of return the favor by saying, once you have this tool for doing influence detection, you can use it to detect the influence of a variable in causing bias in the first place. Because one thing to say there's a problem of bias, it's nothing to say, well, how do I fix it? What input should I eliminate from my data maybe to do this? And so again, this diagnostic tool helps you that. So I think if you see all of these papers, right, at least the ones by Bremen, Hernelius, the second one, which does the joint influence, and this paper, which is by Datta et al., this quantitative influence here, and again, these are all in the course syllabus, you will find that they all have the same idea, right, of doing this random intervention and taking the difference, right? On the other hand, the other paper that I talked about, the one that we wrote, has part of the same idea. It has the idea of taking a difference, for sure. But the way it does the intervention is slightly different. It's not randomized, it's more computational, where you sort of strategically try to remove the influence in an indirect way. And now this the approach that they use in this paper can sort of handle indirect influence in a certain way. There are some subtleties in how they exactly do or don't do it vis-a-vis other works there, which I don't want to get into right here more. Okay. And so that's essentially, this is going to end very early. This is the state of the art on what we know about accountability right now. Okay? At least about influence estimation right now. Let me say that. But a lot of so I'm actually done a little bit early with what I want to tell you about today, but I want to spend a few minutes talking about accountability that's not influence estimation. Right? So I said that the larger question of accountability is about how to understand and assign responsibility and structure to the results of a learning prediction. This is one way to do it, if you have some degree of control over the system. But there's lots of interesting questions, very nice computer science questions about how to do essentially influence estimation and more generally accountability when you don't really have good access to your model. So here's some case studies that people have been looking at. So number one, let's talk about Uber. So, Uber or I guess Ola Cab is also very popular here. They have, let's say Uber for now. There are two things that Uber controls, right? Well, actually, there's really one thing they control. They control pricing. So they control pricing by sort of adjusting the prices up and down in different areas. And you've all heard of surge pricing. So in some places which are very popular, the prices may go up really high. The reason they do it is because they say by increasing the price, because of supply and demand, they'll get more cabs to come in and actually supply people there if there's lots of people who want transportation. So if you're in a hotspot, like yesterday evening, the exams are over, everyone's trying to leave. You think that Uber, if Uber was a presence here, they might say, okay, well, increase the prices now because everyone's leaving, they need transportation. Of course, there are other options. They don't have to do that. But this is what they can control, right? And so if you're a researcher trying to understand how Uber does its work, you'd like to say, hey, what's your algorithm? And they're going to say, I'm not going to tell you. And so the question is, can you find out anyway? Is there a way to find out what Uber is doing or what factors appear to control what Uber is doing when you don't have direct access to their code? And of course, this is exactly the problem we talked about today, right? Influence estimation. Of course, the challenge here is that you don't have as much access to Uber as you do to, say, a black box sitting on a desk somewhere, right? In the case of our neural networks, the chemists are not hiding the neural network from us. They gave it to us. It was just hard to understand. Here, they're probably blocking access as well. So the strategic question of how you issue queries. So in fact, some of the researchers who've done work on this would create fake requests for taxis. And they would see what the price would tell, and they would cancel the request immediately. And they would do this in many different places. So they would do all kinds of work on this and try to figure out what Uber's decision-making process appeared to be. And they haven't really quite figured this out yet, but there's been some interesting, and in fact, some discussions of bias involving in how Uber does pricing in different areas. There seems to be some discrimination going on there, but that's again something that's still being explored. The same thing happened for price discrimination. So you may not be aware of this. I don't know if this happens with, say, Flipkart, but at least with Amazon and a lot of other online retailers, they will look at your browser history, the browser certificate that gets sent out, other information, your IP address, they'll geolocate you. And using that, they will decide what price to tell you. So if you're trying to shop at Amazon or some other big retailer in the US, based on what it can learn about who you are, they might actually present you with a different price. For example, people who surf from Macs appear to get quoted higher prices than people who surf from PCs. One more good thing about a Mac. So yeah, and people who are querying a website from some area that's viewed as a rich area might get quoted a different price than people surfing from a different place. And this was documented. So there are these study guides for exams, that's like the study guides for IIT and the study guides for doing the GRE and for other exams like that. And there's one of these websites, these companies called Princeton Review that makes these books. If you've ever taken any of these exams, you might have sort of seen one of these things. And you can go online and buy the review guides. And it turns out that they were showing different prices to people and appeared to be based on, it seemed to be highly correlated with whether they were Asian or not. So in the US, the Asian community, Chinese, Indian, others are viewed as sort of more academically excelling and more driven to do well. So they were giving them higher prices for study guides because they'll pay the money anyway because they want them. Now, what was more likely happening was some kind of zip code based pricing discrimination. Oh, you're in this area, okay, I'm going to give you this price. And of course, certain areas had a high concentration of Indian or Chinese population, and so they were getting higher prices. Indirect influences again. So in all these cases, these are real cases where you can use the tools of influence estimation in some form or the other to try and understand what these big retailers are doing, because they won't tell you otherwise. And then sometimes you can actually publish the results and shame them into making changes. So one group of researchers found out that Amazon was offering same-day delivery service, but it was very biased towards rich white communities. And they published the results, and Amazon sort of came out and said, oh, we didn't mean to do this. We're going to sort of change the way we decide where to do same-day delivery, blah, blah, blah. And actual change happened as a result of that. So there's a much larger issue of using tools for understanding machine learning models to sort of understand what these black box decision makers are doing. And it turns out some of these things are actually illegal to do in the US. If you're a researcher and you want to sort of create these fake accounts to test what Uber is doing, this could be viewed as fraud and you could be arrested for doing so. And there's a law on the books in the US that basically says that no one's actually ever been prosecuted according to that, but if you interpret the law a certain way, it could be viewed as that. So a bunch of computer scientists have actually sued the government for this law, saying, this law is unfair and for all these reasons. And they're trying to get some exemptions out of it. So it's a very interesting time to be doing this kind of work all over the world, I think. And yeah. So that's all I wanted to say about the larger picture of accountability beyond this, the mathematics of testing a black box, that there are lots of ramifications for doing this. And I think, like I said, even if you have your own models and you want to check them, these are ways to understand what your model is doing. So I planned on having this go on till a bit longer, but I guess we ended early. So I have nothing more to say. So any questions? Yeah.
I guess another interesting area will be to check if a machine learning system is capable, how capable it is.
Mm-hmm.
For example, if the kind of part of the system place to decide who to rate, and then like if there are like some brand, or like if there are secret ways to game the system, so like say if you have like a certain type of parameter, so you won't rate, their friends can like change their activities so that they don't get rated, and other people do.
Right.
So like
Right. So there's been some work on this. There's a paper actually from this year, early this year, called I think the idea here is that there's a game being played between the person trying to classify you and you. So the person trying to classify you is trying to use some metric to decide how to label you. and you want to game the system by changing your attributes to make your label look good, but you don't know what they're doing and they don't know what you're doing. So they need to come up with a labeling scheme that you can't hack, and you need to come up with a way to label yourself so that they'll make you look good. So this is game, and how do you do that in that situation? Right, so there's been some work on how to do this. There's also been work on how to reverse engineer essentially a procedure that's secret. So for example, what every university would love to do is reverse engineer the US News rankings of universities, because everyone knows that's how students apply to universities, and if your university can get your ranking improved, you'll get more students to apply. So that's another thing that people want to do, how to reverse engineer. So US News says, oh, we can't reveal the ranking because then you'll game it. And then the university says, well, but you know, if your ranking is so easily gamed, then it can't be a very good ranking to begin with. And then so on and so forth, right? So I mean, for a long time, for example, the number of publications was a measure of quality. Then people realized you could just publish things in random places and get the counts up. They said, no, you have to look at your H index or how many citations you get, and all these games started happening. So there's an interesting area to think about this whole game theoretic version of doing decision making, and how that might force you to either reveal or not reveal the process being used to make the decision. So, yeah.
What are the basic ideas they use?
I don't remember. Sorry. Any other questions?
The same is what like influence distribution part, the game defined, can be corresponded to the scoring system what China is wanting to introduce.
Which scoring system is it?
China is going to introduce
So for example, for example, what do you have in mind?
an influence estimation part. So told like we actually don't know what things are they, what points are they crediting this for our good work and what points they are cutting from our bad work.
Yes. So can we use influence estimation to figure out? Yeah, it's a very important question, because for sure they're not going to tell you what the function looks like. And so how do you probe such a black box? The problem is, you know, like for example, the Sybil score, right? Now you can actually put, you can go to a website. I was looking at this the other day, and you can go find your Sybil score. Can you create a whole bunch of like fake profiles and then get the Sybil score and use that to figure out what might be happening? So I know that one researcher, for example, has done this in the case of these recidivism prediction models. These models to predict whether someone will commit a crime after being released. These companies that make these models, they keep them secret, but she took the results of these models and then reverse engineered what variables appear to be important, and then used that into some, and built a simple decision tree that does the same thing essentially, using this variable. So yeah, so this is why I think this kind of work is interesting. Yeah, it will be. You mean collecting the data, right? Yeah, it will be. And that's a challenge. That's something. So these areas, the hard part is not doing the influence estimation. The hard part is getting the data in the first place. So every situation is different in its own way. But that makes it, you know, also interesting from a computer science point of view. How do you design anonymous probes into such a system to sort of make this work? Other questions? Okay, a couple of administrative notes. So how are we doing on the list of papers and the projects?
I think one of them has told me what they are going to present.
One.
Yeah, one, and rest of them I think they will get it.
Okay, so you have to present this tomorrow. So maybe it's in your head, but if you haven't actually decided till tonight, that means you don't have much time left to present it. So you really ought to be thinking about this now, so you can tell Abhishek, and so we can do this tomorrow, because you're going to be evaluated tomorrow anyway. So if you show up 5 minutes before, say, oh, I think I'll present this paper, then it's not going to go well for you on your grade. So, and I'm not the one grading because I'm nice. Shekhar's the one grading, right? So yeah, so make sure you get that done. We also have a lab. I said you the thing, and I tested it last night, and things should work. So hopefully, you know.
We'll try and make it.
Yeah. I mean, like I said, even the Python 3.2 things I kind of fixed, so I think it should be fine. So this will be a lab to just a little experiment. So we talked about decision trees yesterday, and we talked about how to put structure into a decision tree to change the way it computes the decision to be maybe less biased or more. So I've actually given you a decision tree code and a couple of data sets which are sort of well known in the community for having biases in them. So I mentioned what the feature is that you're worried about and what the outcome is. So the goal will be to see, okay, run the decision tree with the data set, quantify the bias and statistical discrepancy otherwise, and then apply some of the modifications we talked about, see what you get then, and see if you are able to get any differences in the outcomes. Can you reproduce essentially the results from that paper, or at least some of the results? So you should have enough information to do the whole thing, and you have time. You got today and you got tomorrow to do this, figure this out. And then I want to hear about it next on, I guess, the 2 days, day after tomorrow. Yeah, when I come back and we can talk more about what your experiences were with that. Okay? All right? Okay, cool. I guess we're done early then. So I'll see you in a day and a half, so, or 2 days. Yeah.